Hello everyone. So today we're going to be looking at polynomial functions and looking at key features of said functions. So we're kind of moving into an interesting area because when it comes to polynomials, they come in all shapes and sizes, but it doesn't matter what polynomial you have. It doesn't matter how complex. It doesn't matter how simple. They're going to follow these key ideas, all of them. This is universal, so it doesn't matter what kind of numbers that you use. We're going to see these same general trends. And so we start off with a few definitions. When the first is going to be degree, when we're talking about the degree of a polynomial. I've used this term before in some of the prior videos, but we're going to get a little bit more specific in this. When we're talking about the degree of a polynomial, we're talking about the largest exponent that you see. And if you remember, if you don't see a variable at all, that's the same as having something like, so like in this case, constant, the number 3. If I typed in 3x to the power of 0, the 0, x to the 0 just becomes 1. 1 times 3 is 3. So this is actually could be written as 3x to the 0 without changing it, so this is degree 0. In the case of a line or linear, this is x to the first. When you don't see the exponent, it's understood to be 1. And so this is degree 1. After that, it's a little bit easier to see. The quadratic, this is x squared, so this is degree 2. The cubic, x cubed, that's degree 3. To the fourth, this is your quartic, degree 4, and then quintic is degree 5. It does not matter when we are talking about the degree of a polynomial what the other values are. So even though you have degree 4 in this quartic and degree 2 of the monomials here, this is still just degree 4. So here we just have an example of classifying the polynomials. What are their degrees? Make sure that one of the easier ways to deal with this is to write the polynomial in terms of descending degrees when it comes to each individual term. But you don't have to, like in this case here for number 3. This is still a linear, it's still a degree 1, and the leading coefficient, this leading coefficient, that can sometimes seem a little bit deceptive, as in this case, because the leading coefficient doesn't necessarily come from the leading term depending on how the polynomial is written. The leading coefficient always comes from the term in the polynomial that has the highest degree. So in this case, see, this is a constant, that's degree 0. This is degree 1, which means this is a degree 1 polynomial, and its leading coefficient is this negative 1/2. Right, so is a linear and binomial a factor? We talked about this one in the polynomial division. And so use your synthetic division. If the remainder is non-zero, it is not a factor. And if it is, okay, so here's 2 problems you can try on your own. And so then if you look at this, then we're kind of combining two things into one when we're talking about the synthetic substitution. First off, the x plus 2, is that a factor? Is that a factor of this polynomial here? And when we go through the synthetic division, we find out that it is not actually a factor. But then, in addition to that, we can also evaluate for the polynomial when p is negative 2. So we would know that the evaluation of this function at negative 2 is also going to be 25. So we're killing 2 birds with 1 stone in terms of this one. Same thing here, where okay, is this a factor? Then when you go through the proper process to find your a value that we spoke about in the prior video, then you get a remainder of 0, which means that this value is indeed a factor, and in addition to that, we can substitute, or sorry, we also get the result of 0 when we evaluate for 2. Now, one thing that was done here that's a little bit different than what we did in one of the prior videos. If you look at these numbers and where they came from, that comes from up here. When solving for the a value, when taking this binomial, setting it equal to 0, solving for x in order to get that a value, we ended up having to divide by 3. And so those coefficients come from dividing this polynomial by 3. 3 divided by 3 is 1. Negative 6 divided by 3 is negative 2. 6 divided by 3 is 2. 3 divided by 3 is 1. And negative 30 divided by 3 is negative 10. In the prior video, and some of the ways that I will work this is I will use the synthetic division, and then once I get to this result, then I would have divided by 3, but I left the coefficient as the original, and you still get to the same answer either way. And so then the choice is going to be yours on that. Another thing, well, actually, I'll hold that comment for a later video. Okay, now we're talking about what we're leading to is solving polynomials, solving rational equations. And so we're trying to find when x is equal to 0. And the best thing to do whenever you're dealing with any kind of polynomial is to try and factor things down as far as you can. The more that you can factor, the easier the problem is going to be to solve. So we're looking at another example of factoring by grouping. And so what you look for common items. You look for commonalities. Both of these terms here have 25. So if I factor out a 25, and I can take it a step further, factor out a negative 25, then this becomes that when you factor out the 25. And I'm only doing it to part of it, because then what I'm looking for is there an x minus 1 component here? If I factor out the x squared, I also get this x minus 1. And so what we have is the distributive property. This is x minus 1 times some value, and then x minus 1 times another value. So then these values here, the x squared and the minus 25, make up another binomial that has been multiplied by by x minus 1. This is a difference of squares which further factors down, and so we can factor polynomials down into as many separate components as we possibly can. If you go as far as to use complex numbers, whatever the degree of the polynomial is, you can always factor it down into that many terms. So this is degree 3. It has 3 factors, but they may not all be real. It has 3 complex factors, so that's your imaginary number I, but they may not all be real. This is a case where all of the factors were real, and so we were able to factor it down. A quick check to make sure if you're right is graph your original, and then graph each step by adding in these parentheses. Did that change the graphing? No. By factoring out the x squared from the front and factoring out a negative 25 from the last 2 terms, the graphs are going to overlap. The graphs are going to overlap, and then finally the graphs are going to overlap. So that means that you have the same, you're finishing with the same equation that you started with. Another check is using the tables in the calculator. Okay, and you can do the same thing here. The numbers should be identical. So you can try this one on your own, and then you get down here to your solution. This is also just demonstrating how you can check using the graphing calculator. You can check by using the graphs themselves in Desmos, or there are ways you can convert functions into tables in Desmos, and you can check them that way as well. Probably will not do that in any of these videos. That's something that you can ask your instructor if that's something that you would like to see. Okay, here's another one you can try on your own. Notice in this case you have a leading coefficient that is not 1, but that's okay because you're still solving the problems in the same manner. What I would suggest anytime that you're looking at a potential factor by grouping is like look at your terms. Look at your terms. Those are both obviously divisible by 4, and so then that would give the result of 2x plus 1. Then you ask yourself, can I create 2x plus 1 out of this function? And that helps, that can help you see, okay, well, then the factor I'm looking for is x squared. Everybody has their own technique, and that is entirely up to you. I'm just throwing in my 2 cents on the matter. Now we want to look at the multiple roots. What happens if a factor occurs more than once? So we're given this particular factor, and sorry, in this case, this is actually an equation, and all 3 of these terms have at a minimum x cubed, and they're all also divisible by 3, so they all have a factor of 3x cubed. Once you do that, this is perfect square, so this is x plus 3 times x plus 3. Then you can see my 5 different factors here. I get the roots, I get repeated roots of 0, 0, 0, and -3 and -3. And so this is what is known as multiplicity, where a single root occurs multiple times. So in this case, since the x is 0, comes up 3 times, 0 has a multiplicity of 3, and since the -3 appeared twice as a root, then it has multiplicity of 2. Anytime that you have an even multiplicity, you're going to see a graph reflection on the x-axis. And if you have an odd multiplicity, you're going to see an intersection with the x-axis. If it's a multiplicity greater than 1 and odd, then there's going to be a bend. It's not going to be like a straight line that goes through it or a straight curve. There's going to be a bend in the curve. So you can see here it's not entirely straight. So this statement here, you cannot always determine the multiplicity of a root from a graph. First thing, you can tell where one root is going to lie. So I see -3, I can use synthetic division, I can work backwards. If the root is -3, so if x is equal to 3, that means, if x is equal to a -3, that means that the binomial is x plus 3. I can factor that out, and then I can graph, and I'll show a case of this in a minute, and I'll use this problem, how you can work backwards and help you find your multiplicity. But what this statement means is, like, I see that there is a reflection here at x is -3, but I don't know if that has occurred. I know it because it's a reflection. It has to occur an even number of times, but I don't know if it's 2, I don't know if it's 4, I don't know if it's 6. So you still have to do the algebra work in order to come up with a solution. I'm going to switch over. I'm going to take this problem and I'm going to show you how you can kind of work your way backwards into solving these problems. Okay, so there's a couple of things that are going to come into play on this when going through the problem. First thing that I want to say is, when we're talking about factors, we can approach this a couple of different ways. So I'm going to start with just a number, just to give you kind of an idea about what's going on, and then we're going to go from there. So I'm going to take something like 100. And if I were to say, what number is 100 divisible by? And you may say something like 2, because 2 times 50 is equal to 100. Then I could then take a look at 50 and say, well, what is 50 divisible by? And you may say it's divisible by 5, because 5 times 10 is equal to 100. And the thing about if 5 is a factor of 50 and 50 is a factor of 100, then it has to be true that 5 is also a factor of 100, which of course it is, because 100 divided by 5 is 20. And so we're going to use the idea of that a factor of a factor is the original when it comes to solving some of these problems. So I want to clear that up, and we're going to take a look at this problem. And so I'm going to move through this one fairly quickly, but I start looking at, okay, what can I do? What can I do to simplify this problem? And I see I have a 3, I have an 18, and I have a 27. And so that tells me that all of these terms are divisible by 3. And so then this is x to the 5th plus 3 times what is 18, so that's going to be 6. And so that's 6x to the 4th. And then 3 times what is 27? Well, that is 9. And so then this is 9x cubed. And I know that at least this part of everything is correct, because I factored I factored out a 3, but my graphs still overlap one another. So now I want to take this a step further. I see every one of these terms have an x, and so I'm going to factor out an x. Now when I just do that, see how my graph changes. That means I've changed the equation. But when I factor out an x, I end up having to reduce all of these numbers. I have to reduce all of my powers by 1, because I've removed a 1x. And you can go through the long division however you want to get to this process, and then arrive at your answers there. Now in this next one, so I kind of left it as is. I know that in the prior page they started off with 3x cubed, and I'm going to work my way there, but I just want to show you how this is going to look using something like synthetic division. So I get to this point, so my graphs overlap, and so, but the thing is that if I know that 3x is a factor, and let me go ahead and put that in parentheses, and I know that this number is a factor, then any factor of what I have already highlighted is also going to be a factor. So I'm actually going to put this into a new line, but the thing is I'm always going to come back to it. Okay, so I'm putting this in a new line, and I get this different graph. But you see, I still have these factors going on, and so now I get to choose. I'm going to go with this. I'm going to go with this -3. I'm going to go with this -3, and so then I go into my synthetic division. This is a root. This is a root of -3, and I had set this up kind of one step early. Okay, so now I'm going to look at my coefficients. This is 1 for x cubed, so this is 1 for x cubed, and plus 6x cubed, and plus 9x squared, plus 0x plus constant. And then I'm going to synthetically divide. So I bring down the 1. 1 times -3 is -3. 6 minus 3 is 3. 3 times -3 is a -9. And 9 minus 9 is 0. Times -3 is 0. 0 plus 0 is 0. Times -3 is 0. And 0 plus 0 is 0. So this is indeed a factor. This number right here is a factor. And well, let me change. Okay, I hope this thing says. So this is a factor, but if x equals -3 was the root, well, if I add 3 to both sides, so now this is -3 plus 3, which of course -3 plus 3 is going to be 0. My factor is now x plus 3. So if I go in and type in this x plus 3, I take a look at what is I take a look at what is left here. So I'm going to take a look at what is left, and I started off with x to the 4th, so this is now x cubed x squared. I'm always going one less. I'm always going one less than prior. This is x, and this is my constant. And so I'm just going to copy this over. Okay, so what I'm left with is 1x cubed plus 3x squared plus 0x plus 0. So if I change this to 1x cubed plus 3x squared plus 3x squared plus 0x, then I should end up with the same graphs as the original. So what I've done is I've factored this down. I've factored this down a little bit further. What happens if so now I need to take a look at this. Can I factor this anymore? So I'm separating it. Now I'm just looking at this piece. I see multiple roots. I see a root at -3. That's got to be an odd multiplicity because there's some kind of an intersection. And I see a root at 0. That's got to be some kind of an even multiplicity, and because it reflects. So let's just pick 0 this time because I can't. No other reason. So I'm going to pick 0 this time, and I'm hoping maybe this format. Maybe it'll keep the format of this. All right, so I'm going to go with 0. Let me change the format just a little bit here. I'm trying to do this quickly, so forgive me if it messes up. Now I repeat. So bring down to 1. And 1 times 0 is 0. 0 plus 3 plus 0 is 3. 3 times 0 is 0. 0 plus 0 is 0. 0 times 0 is 0, and I still end up with this remainder. I still end up with this remainder being 0. So 0 is indeed a factor, and which, if you do x equals 0, you can just x is going to be all that you need. So I'm going to bring in x. Bring in x here. Sorry about that. And now this is so I'm dropping. I'm reducing my powers by 1. This was x cubed, so this is going to be x squared, x, and then your constant. So this is 1x squared plus x plus 3x plus 0. So 1x squared plus 3x. Here's my original, and now they're the same. And then you just continue whittling this down until finally you get this factored as far as you can go, at least within the real number. So now not only is this factored, but I also know all of my roots. I get to 0, 0, 0, -3, -3. Okay, so now determine the roots of each equation and multiply by each root. And so you should have come up with these answers here. Feel free to try this one on your own. Here's another one that you can try on your own. All right, now we're going to talk about end behavior. So when we're talking about the end behavior of a graph, we are talking about what happens as x gets incredibly large in both directions. What happens when x moves towards positive infinity, and what happens when x moves to negative infinity. And even though there are, technically an infinite number of polynomials that we can have, every single polynomial, no matter how complex looking, is going to fall into essentially 4 categories, and they are determined by the degree and the leading coefficient of the polynomial function to determine its end behavior. And this is it. If it's an odd degree polynomial, so if your largest exponent is odd, so whether it's 1, 3, 5, or anything higher, if it's odd, it's going to have at some point some kind of a curvature that allows it to either start off in the negative direction towards negative infinity and finish in the positive direction towards positive infinity, or vice versa. It's going to start off at positive infinity, and then it's going to decrease forever and ever into negative infinity. And that is controlled by whether or not the leading coefficient, so the number that's associated with the highest power, is positive or whether it's negative. If it's negative, you start high, you end low, and if it's positive, you start low, you end high. If it's an even degree polynomial, so 2, 4, 6, 8, etc., even degree, and then you're either going to start at positive infinity and end at positive infinity, or you're going to start at negative infinity and end at negative infinity. Now, there's lots of stuff that can happen in between, but when talking about end behavior, it's only these 4 cases. So when your leading coefficient is positive, then if it's an odd degree, it follows this format, and if it's an even degree, it's going to follow this format here in the upper right. If your leading coefficient is negative, if it's an odd degree, it's going to follow the lower left, and if it's an even degree, it's going to follow the lower right. And so there's a lot that we can tell about a polynomial function really without actually graphing it. I mean, we're going to use graph to verify what we're doing, but we already have kind of an idea about how things are going to look. So in this case, does this function have an even or odd degree, and then whether or not the coefficient is positive or negative. So I start off at positive infinity, and then it trends downward. I mean, yes, here in the middle, close to 0, it changes its direction, but it still finishes continuing down at negative infinity. So that tells me it's going to be an odd degree polynomial, and since it started off at positive infinity and finishes at negative, this leading coefficient is going to be negative. And I look down here, and guess what? Okay, that's exactly what we said. And because even though there's a lot of different stuff that's going on here, it still follows this trend here. What about this one? Which one is it going to be? Try this one on your own. And what you should see is it starts off at positive infinity, and it's going to continue on towards positive infinity after coming down for a little while. That's an even degree polynomial. And since it's both positive infinity in both cases, that means that the leading coefficient is also positive. Now we have turning points. The short answer, like if you go back and you look at, say, for instance, this one. So there's a root here that's close to -1, and then there's another root at 0, and then there's another root at close to +1. The only way that you can have an intersection at -1, 0, and again at +1 is that the graph has to change its direction twice. And so that's what we mean by a turning point. So these turning points create local or relative maximums and minimums. And so you're looking at it as if, you're narrowing your window. So like right here, that's a local maximum. It doesn't mean that it's the absolute highest point of the graph, but it means it's the highest point of the graph at this location. It's a turning point. Here, in this region only could be considered a relative minimum because it's a turning point, but then when you compare it to the entire graph, you see that it is actually the single lowest point, and so this is now it's not the relative minimum, but it's the global or absolute minimum. Same thing here. If we're just looking at only this part of the graph, do we know whether it's a relative maximum or a global maximum? Well, we don't unless you compare it to the entire graph. this here. This one is going to be a local minimum. I don't know why the graph's kind of acting that way right now. This turns out to be a local minimum because it is indeed a minimum in this region, but it is not the most minimum across the entire graph. So for any graph, there's only one global maximum and minimum, but you can have multiple maximum points or minimum points, which we refer to as maxima, or minima. So given these two graphs, find the local max, the local maxima, the local minima. So here, there's a local, there is a minima that occurs here. There's a minima that occurs here. So that's these two. But of these two, at best, only one of them can be the absolute minimum, and -4 is less than -1. So the absolute minimum is -4. The local maxima, there's a little bit of a typo here. That should be 2, because there's a local maximum right here. So that 0, ignore that. This should be a 2. And but when we're talking about the absolute maximum values, the thing about maximum and minimum is that we have to take into consideration the end behavior as well. So this has an absolute maximum at positive infinity. And then there are zeros that occur at -3, 2, and 5. For this graph, let's see here, we'll go with the maxima first. So there is a maxima, and there is a maxima. So there is a maxima. This should be about 6.5 instead of 1.5. And so minima, you're going to have a minimum here at -5. You're going to have, okay, I see what they did. You're going to have a minima at 1.5. You're going to have a minima at -5, and this graph actually terminates, and so there's another minima here at about 7, or a little bit after 7. There is a termination point here, and this turns out to be its maximum point at -6, and because these are bounded, so absolute maximum, okay, of all of these. So this one just had, I think they started rushing through this one a little bit too much. Absolute maximum here, absolute minimum down here in these cases. And then you have your zeros. Now the zeros for this one are correct. Okay. Sorry about that last problem, but I hope all of this works for you, and we look forward to seeing you in the next video.